In this session, we will learn how to solve differential equations in Scilab. We will learn how to solve linear first and second order differential equations using ODE method. Then we will learn to solve higher order linear equations with constant coefficients. A differential equation is any equation which contains derivatives, either ordinary derivatives or partial derivatives. Differential equation with only one unknown variable is called ordinary differential equation. We know that order of a differential equation is the largest derivative present in the equation. Here in the equation, we have derivative of a function with respect to y with order 1, so it is called first order ODE. An ODE, together with an initial condition, is called an initial value problem. Initial conditions are values of the solution, or its derivatives at specific points. In this kind of problems, initial condition at some point x0 is used in the general solution of the equation to obtain the final unique solution. ODE is the ordinary differential equation solver available in Scilab. It automatically selects between non-stiff predictor corrector Adams method and stiff backward differentiation formula method. ODE function has a specific syntax where y0 is the vector of initial conditions at time t0. T is the vector of times at which the solution y is computed, and y is matrix of solution vectors. In the ODE function, we have to pass reference to a function f that forms the right-hand side of the differential equation. This function f is a Scilab function and should have the syntax as y dot is equal to function of t and y, where y dot is the first order derivative which we are calculating. Now, let's solve a simple problem to understand the process of solving the ODE. Here, we have a first order ODE with an initial condition specified. Let's see how to solve this in Scilab. Here, we first define the function f, where we define the differential equation and return it in y dot. Function f should always have parameters t and y as inputs. Then, we define the initial data required to solve the equation. Time vector t is defined using colon operator, in a range starting from 2 to 2.5 and steps of 0.05. Then, we call the ODE function with all the data, and get the results of numerical differentiation in y. We then plot the graph of y against t. Now, we consider nth-order initial value problem. We will consider homogeneous equations, where right-hand side function g is 0. For solving higher-order homogeneous equations, we can use auxiliary equation method. In this method, we form a polynomial equation from the coefficients of the auxiliary equation, and then find the roots of the equation. We can then form the general solution of the differential equation using the roots. Values of the constants can be found from initial conditions. Then we can evaluate the equation and plot the graph. For non-homogeneous differential equations, apart from calculating the roots from auxiliary equation, we also need to calculate particular solution to get the complete solution of the differential equation. It is a complex process, and to avoid it, we convert the higher order equation into a system of first order differential equations, and solve the system using ODE solver. Now, consider the second order equation shown. We keep the highest order term on left side, and move all other terms to the right side. Then, we create two variables y1 and y2. y1 is equal to y, and y2 is derivative of y. Then, we differentiate y1 and y2, which forms the system of first-order equations, for our second-order equation. Now, let's see it in Scilab. Here, we define the function f, the output variable yd is a list, which returns results of two equations back to the ODE solver. In the initial condition vector y0, we specify initial values for the equation at y0 and y'0. Then, we call the ODE solver with all the data, and get the solution. From the graph, we can see that the curve starts from y equals -1, which is the initial condition for the solution. Now, we consider a spring mass system which has a non-homogeneous second-order equation of motion. The external force is a function of time. Let's see how to solve it in Scilab. Now, in the y-dot function definition, we include two input arguments, k and m, which are spring stiffness constant and mass. Then, we define the variable pt, and calculate the time-varying force. Then, we calculate the differential equations and return results to ODE solver. In the ODE solver function, we pass a list variable, which has the function reference, spring stiffness, and mass as parameters. Now we run the script. In the graph of the solution, we observe that, when time is less than 2 seconds the displacement of the mass increases, and after 2 seconds the force is constant, and mass undergoes simple harmonic motion. That brings us to the end of this session. Thank you for your interest and attention.